Hi everyone, I'm Xueren. Today I'm going to talk about our paper DKEC Domain Knowledge Enhanced Multi-Label Classification for Electronic Health Records. So we hope to develop a language model to help the doctor to do the diagnosis prediction based on the electronic health records, but there are several challenges such as long-tail distribution as shown in the picture, and also have a multi-label text classification, basically multi-diagnosis code. They co-occur with each other, and we propose to use the domain knowledge to solve the problem because we believe domain knowledge can compensate for the data scarcity and also have the relation constraints. One line of the research focuses on incorporate the domain knowledge in the pre-training stage like BioBird, Gigatron, and the BioMed-ALM. Other works also incorporate the domain knowledge by the semantic meaning of the labels or the hierarchical label structures into the model for the diagnosis prediction. However, there are several common limitations of the existing work that they either incorporate the domain knowledge in the pre-training stage, or they only incorporate the domain knowledge, which is the hierarchical graph, by the label-wise attention into the convolutional neural networks. In this work, we incorporate the heterogeneous graph by the label-wise attention into multi-filter convolutional neural networks and also the transformers. To conclude, our contribution is we have a knowledge graph construction by the GPT-4 with chain of thought prompts. And we incorporate the knowledge graph with different language models by heterogeneous label-wise attention to improve the performance. And furthermore, we show the DKEC outperform the state-of-art on 2 real-world datasets and enable small language model to achieve comparable performance to large language models. Our DKEC pipeline includes the knowledge graph construction and the graph branch, and also the text branch, and the heterogeneous label-wise attention and the classification module. Next, we will divide every module one by one. So first is the knowledge graph construction. So as you can see from the picture, every diagnosis code will have a short text description, and we use it as the query for the API or the web driver from the Wikipedia or the Mayo Clinic website to get the text content relevant to this short description. And then we design a GPT-4 chain of thought prompt to help to extract the signs and symptoms and treatments from the text. Specifically, we use the chain of thought prompt, but divided the task into 3 small different tasks like token classification, span detection, and the relation extraction. So for the token classification, we'll label every token its symptom, treatment, or nothing. And for the span detection, it will concatenate consecutive words into a medical phrase. And for the relation extraction, we aim to avoid some scenarios like negation in the text. And the output of the GPT-4, we use the UMLs to do a medical concept normalization based on the defined semantic types. And we get the knowledge graph from each knowledge base, and we do a union of all of the knowledge graphs. For the heterogeneous graph, we have 4 different types of node like diagnosis, symptom, treatment, and the hierarchy. And we have 3 different types of edges between diagnosis code with the signs and symptoms and diagnosis code with the treatment, diagnosis code with the hierarchy. And we have the embedding initialization by pre-trained birds using the overview of the diagnosis code or the name of the medical entities. In the graph branch, the input is a knowledge graph with initial node embedding, and we train the heterogeneous graph transformer to get the updated diagnosis code embeddings. In the text branch, we use a text pre-processing to remove the punctuations and the stop words and then send it into the long document encoder like the multi-filter scene or pre-trained transformers to get the document representation. And then we design the heterogeneous label-wise attention, basically given a document representation and the label representation. We derive the label-wise attention vectors by using the formulas. So basically it shows how the case label assign different weights for each token in the document representation. And then we derive the label attentive text representation to measure how informative document is for all the AR labels. For the classification module, we use a Boolean and a linear layer to derive the probability over all the diagnosis code, and we use the binary cross-entropy loss in our training. So we aim to do the experiment to answer the following 3 research questions. So the first research question is, can our model DKEC improve the multi-label text classification performance for the class imbalance datasets? And the second is, how does DKEC perform when applied to different language models with varying sizes? And the third is, how does the DKEC perform with scaling label size? Here is an overview of our datasets and the knowledge bases. So we use 2 datasets. The first is the Emergency Medical Service, which is a privately collection of 4,000 pre-hospital EPCR annotated with the EMS protocols. The knowledge base is the ODEMSA documents. And the other is the MIMIC3 dataset, which is a real-world EHR dataset annotated with the IC9 diagnosis code. It have the Wikipedia and the Mayo Clinic to build the knowledge graph. And the table shows the statistics of the dataset. We further divide our label by frequency into head, middle, and tail labels. Here we first do the qualitative evaluation for our knowledge graph. To do that, we manually annotate the signs and symptoms and treatments for 50 IC9 codes, which is evenly sampled from the head, middle, and tail labels. And also we do it for 43 EMS protocols. And we compared with our 1 short chain of thought GPT-4 methods with 0 short GPT-4 methods and some ML-based methods like SciSpaCy and rule-based like CTAKes and MetaMap. And the results shows that our chain of thought prompt GPT-4 outperformed the other baselines in medical entity extraction consistently by a considerable margin. So how does DKEC perform on the class imbalance datasets? On the head labels, compared with the state-of-art, we find it have minor improvements. In the middle labels, there are more improvements compared with the head labels. And the most dominant improvements occurs in the tail labels. In the overall performance, we find the DKEC maintain the performance in the head labels but have more improvements in the middle and tail labels, which elevate the class imbalance problem. And next, we apply our DKEC to different sizes of language models, and we find performance of DKEC-based models increase less as model size grows. And the second finding is we find the DKEC enables small language models achieve comparable performance with the large language model, which is very useful for resource-constrained devices. And then we apply our DKEC model on different scaling label sizes. And we find with the increase of number of labels, the multi-label text classification generally drops, but the DKEC help to maintain the performance compared with the state-of-art, especially when the external knowledge are available for all of the model labels. And we also do an application study to conduct experiments to study the effectiveness of the DKEC. We find the DKEC can outperform the state-of-arts that only use the label hierarchy. And also we study what's the most important information in the DKEC. We find by removing the label hierarchy, it actually didn't have too much influence on the performance. So the finding is the external knowledge is more important for performance improvement. So there are several limitations in our work. So first, we only find part of the diagnosis that have the knowledge. And the second is the accuracy of the full knowledge graph will require a large amount of human efforts. And the third is DKEC and the other baseline study in this paper can only be used as a reference rather than final decision for the patients in the real life. And thanks to all my co-authors, and our project is funded by NIST project, and here's our GitHub code. Thank you.